Hey everyone, in this video we're going to learn about arithmetic sequences. An arithmetic sequence is a sequence in which the common difference, d, is added to each term to get the next term in the sequence. So an example of an arithmetic sequence is 5, 10, 15, 20, 25, continuing on. If we look to get from one term to the next, we have to add 5. And to go from 10 to 15, we have to add 5. 15 to 20, add 5. 20 to 25, add 5. So we're adding 5 each time to go from one term to the next. So the common difference, which we denote with a lowercase d, in this sequence is equal to 5. Now, if we look back at the definition, it only says added, but subtracted can be included here as well. We just think of subtraction as addition of a negative number. So any sequence where we're either adding or subtracting the same amount to get from one term to the next is an arithmetic sequence. Determine if the following sequences are arithmetic. If they are, state their common difference. So the first thing we have to be able to do is correctly identify arithmetic sequences. So the first sequence, 7, 10, 13, 16, 19, if we look from term to term, let's see, add 3, let's see if that holds. 10 to 13, add 3, 13 to 16, add 3, 16 to 19, add 3. So we are consistent, we're adding 3 to go from one term to the next. So this sequence is arithmetic, and the common difference is 3. Our next example, -2, 4, -8, 16, -32, continuing on. So there it looks to go from one term to the next by multiplying -2. And multiplying -2, and I continue on, but what I should notice right away then is that it is not an arithmetic sequence. Not arithmetic. We are multiplying the same value over and over again to get from one term to the next. But the definition of an arithmetic is addition or subtraction, adding or subtracting that value. This sequence is actually called geometric, and we're going to handle that in a later video. Our next sequence, 1, 2, 4, 7, 11, continuing on. If we compare to get from 1 to 2, we add 1. 2 to 4, we add 2. 4 to 7, we add 3. 7 to 11, we add 4. So there definitely is a pattern. We're adding to get from one term to the next, but we're not adding the same amount each time. So because of that, this is not an arithmetic sequence. There's definitely a pattern, but we're not adding the same value every time. Now, starting the sequence again, some of you might have noticed we could have started by multiplying 2, right? 1 times 2 is 2, 2 times 2 is 4, 4 times 2 then would be 8, and this is 7. So that's not consistent through all of the terms that they've given us. And our last sequence, 4, -2, -8, -14, -20, continuing on. So to get from 4 to -2, we subtract 6. -2 to -8, we subtract 6. -8 to -14, subtract 6. -14 to -20, we subtract 6. So we are subtracting the same amount to go from one term to the next. So this sequence is arithmetic. And the common difference is -6. So now that we've practiced identifying an arithmetic sequence, we have to learn how to write it out mathematically. Well, in order to do that, first let's answer a few questions. What type of function increases or decreases by a common difference over equal intervals? Okay, so what type of function do we add or subtract the same amount as we go over on an interval? Well, that would be a linear function. And this is something that we discussed when we were comparing linear and exponential functions to one another. Right? A linear function has a slope, which means that it increases or decreases by the same amount over a given interval. Right? A slope of 3 means we add 3 to the y value as we go over 1 on the x, and that stays consistent time and time again. So point slope form of a line, as a refresher, is y minus y1 equals m times x minus x1. So in the point slope form of a line, which variable would represent the common difference if we were going to use it for a sequence? Well, the common difference is the value we add to go from one term to the next. And the slope we just discussed is what we add or subtract to the y value as we go over on a set x interval. Right, that slope of 3 again, we add 3 to y as we go over 1 on the x. So the slope would represent the common difference. Okay, so m, or the slope. So now that we've established that connection between the slope of a linear function and the common difference, we can write the equation of an arithmetic sequence with a linear function. And that's the key idea here. We can write the equation of an arithmetic sequence with a linear function. Now before we look at that, we need to define an explicit formula. An explicit formula allows you to find the value of the nth term directly without using a previous term. So now we have two different ways we can write a sequence. A recursive formula, remember that required us to define the first term and define a sub n in terms of a sub n minus 1 and whatever pattern we established. Really good for identifying the pattern and the first term. Recursive is really bad if we're trying to find the 100th term. Because to find the 100th term, I need the 99th term. And it kind of spills all the way back. An explicit formula is saying, if I want the 100th term, I just have to plug in 100, and I would get the 100th term out. So that's the advantage of an explicit formula over the recursive formula that we already know. So an arithmetic sequence can be modeled by a linear function with a domain of whole numbers. Now the domain piece, remember when we wrote out the n values under the blank spaces in the previous video, that was our domain. So our domain was either 1, 2, 3, 4, 5, or we looked at that one example where n started at 0, and it was 0, 1, 2, 3, 4. So that's why we had to say the domain is the whole numbers. So these are the n values here. Now, point slope form of a line, y minus y1 equals m times the quantity x minus x1. So if I replace x's and y's with sequence notation, right, our subscript notation, that's going to become a sub n minus a sub 1 equals d, which is the common difference, times n minus 1. Typically, they're going to have us write this as a sub n equals a sub 1 plus d times n minus 1. Notice we're using the first term a sub 1, so in our parentheses, it's n minus 1. Right? We can think of this as having the point 1 comma a sub 1 on the line. Actually, let me write that in a different color so it stands out. Right? We can think of having 1 comma a sub 1 on the line. The nice thing about understanding that this is nothing more than point slope is the flexibility. Let's say we don't have the first term. Let's say we had the 6th term of the sequence. Well, then I can write a sub n minus a sub 6 equals the common difference times n minus 6. And then a sub n would be equal to a sub 6 plus the common difference times n minus 6. I don't always need the first term then. I can use really any term of the sequence. Now, if we have the first term, that's the simplest. So now that we've established that connection between point slope form of a line and the explicit formula for an arithmetic sequence, let's practice writing out the formula for a few arithmetic sequences. Suppose an arithmetic sequence has a common difference of 2 and a first term of 11. Use the point slope form of a line to create an explicit formula to represent the value of the nth term of the sequence. Okay, so common difference is 2, so d equals 2. First term is 11, so in subscript notation, a sub 1 equals 11. So I can think of this as a point, if I want. I can think of it as the point 1 comma 11, right? N comma, again, I'll change colors here. N comma a sub n, if you will, for the point. So then, using point slope form, a sub n minus 11 equals, common difference is our slope, so 2 times n minus 1. And typically they have us write it as a sub n equals, so 11 plus 2 times n minus 1. It's essentially writing it in y equals form. Now, here's something I want to point out. Don't forget your order of operations. You need to do this multiplication first before you add it to 11. A lot of times I see students do 11 plus 2 and then multiply. Just be real careful there. So use the explicit formula to find the value of the 15th term. So that means n equals 15. So we're going to plug 15 in for n in our formula. So a sub 15 equals 11 plus 2 times 15 minus 1. So a sub 15 is 11 plus 2 times 14. So a sub 15 is 11 plus 28, which is equal to 39. So the 15th term of the sequence is 39. And it's as simple as that. Plug in n equals 15, we get the 15th term. And again, I'm just going to compare it quickly to recursive. Recursive formula to find the 15th term, I start with the first term, get the second, then get the third, and I keep working all the way till 15. Definitely a lot more time consuming. This one, we get our explicit formula, plug 15 in, and we get the number that would be in our sequence. Write an explicit formula to find the nth term in the following arithmetic sequences. Assume n is greater than or equal to 1. So for simplicity's sake, we're always going to assume that this first term is n equals 1. So 7, 10, 13, 16, 19. So we said that this sequence has a common difference of 3. We looked at that already. And we can treat this first term, if we want, we can write it as a point, 1 comma 7. Right? Because a sub 1 equals 7. If I want, I can write it as a point. So writing out the explicit formula for this sequence, a sub n minus 7 equals 3 times n minus 1. Again, we want a sub n equals, so a sub n equals 7 plus 3 times n minus 1. In our next sequence, we already established that the common difference was negative 6 in an earlier example. And the first term, a sub 1, is equal to 4. So if we write this as a point, it would be 1 comma 4. So a sub n minus 4 equals negative 6 times n minus 1. Right, I have a slope. It's now the common difference. I have a point. And a sub n equals 4 minus 6 times n minus 1. So there we have the explicit formula for each of these sequences. Now write an explicit formula to find the nth term in the following recursively defined arithmetic sequences. Assume you are given the initial term of the sequence. So this is nice because we're going to start with a recursive and end with an explicit. So the in-between step here that I would do is write out a few terms of the sequence. So we have a recursive formula here. So the first term is negative 2. And then if we look at the second equation, it's saying to find the next term, a sub n, take the previous term and subtract 10. So the next term, if we subtract 10, would be negative 12, and then negative 22, negative 32, negative 42. So there we have our arithmetic sequence, or at least 5 terms of it, right? It continues on. So the common difference here, well, how do we get from one term to the next? We subtracted 10. The common difference was negative 10. And the first term, a sub 1 equals negative 2, which we can write as the point 1, negative 2. So we have a slope, the common difference. We have a point. So a sub n plus 2 equals negative 10 times n minus 1. So a sub n equals negative 2 minus 10 times n minus 1. Our next sequence, a sub n plus 1 equals a sub n plus 1/4. And need that a sub 1. A sub 1 equals 31. Okay, so our first term is 31. And then our recursive formula, the second equation, is saying to find the next term, a sub n plus 1 here. take the previous term and add 1/4. So I'll use mixed numbers here. So the next term would be 31 1/4. After that, 31 2/4, which is 1/2. Then 31 3/4, and then 32. And then that sequence continues on. So our common difference is 1/4. Our first term is 31, which written as a point would be 1, 31, right? N and a sub n. So when n equals 1, that first term is 31. So our explicit formula is a sub n minus 31 equals 1/4 times n minus 1. So a sub n equals 31 plus 1/4 times n minus 1. Now write a recursive formula for each of the following explicitly defined arithmetic sequences. Assume n is greater than or equal to 1. So here they're giving us the explicit formula now, and we need to come up with the recursive. Okay, so again I would start by listing out the first 5 terms. Now just as I did with recursive, I'm going to start by just creating 5 blank spaces here. And underneath write their n values. So here n equals 1, 2, 3, 4, 5. So to find the first term of the sequence, we have to plug in n equals 1. So it would be a sub 1 equals 12 minus 9 times 1 minus 1. So that's 12 minus 9 times 0, which is 12. And then to find the next term, a sub 2, that would be 12 minus 9 times 2 minus 1, which is 12 minus 9 times 1. 12 minus 9 is 3. And then we keep going. A sub 3 equals 12 minus 9 times 3 minus 1. So 12 minus 9 times 2. So 12 minus 18, that's negative 6. Now at this point, I think we can see what the common difference is to finish it off. But this is just a great example of how we find a given term with an explicit formula. We plug in a specific n value. Now we should notice the common difference is negative 9. So continuing, we'd have negative 15 and negative 24. So our recursive definition, so we need our first term, so a sub 1 is 12. And then a sub n, if I want the next term of the sequence, I take the term before it, which is a sub n minus 1. And we notice the common difference was 9. So we subtract 9. So here we have the recursive definition of this sequence. So next we have a sub n equals 3n plus 1. All they've done here is they've simplified that point-slope form, so it looks more like slope-intercept form. So we're actually seeing it done in 2 different ways. So again, we can list out the first 5 terms of the sequence. So n equals 1, 2, 3, 4, 5. So to find the first term, we're going to plug n equals 1 in. So that's 3 times 1 plus 1, which is 4. So our first term is 4. Second term is 3 times 2 plus 1, so that's 7. Our third term is 3 times 3 plus 1, so that's 10. And we should notice at this point the common difference is 3, so 13 and 16. In both these cases, I want to point out, what was the common difference? It was the slope of the line. And if we notice that right away, we can use that to our advantage. In this case, we'd have to plug 1 in regardless to get that first term. Here, since we have n minus 1, we could have recognized that 12 would have been the first term. Now we need to write this recursively. So start with an initial value. So a sub 1 is equal to 4. So that's our starting value. And then here I'll use a sub n plus 1. So to find the next term of the sequence, I use the term before, which is a sub n. And the common difference here was to add 3. So here we have the recursive definition of this same sequence. All right, so in this case, we started explicitly, ended with a recursive definition, and previously we started recursively, ended with the explicit definition. So our last example for this video, let's start with a sequence and do both. Write both an explicit formula and a recursive formula to find the nth term in the following arithmetic sequence. Assume that n is greater than or equal to 1. So explicitly, first we'll define our common difference, and we'll need that for both of these. So 10, 9.5, 9, 8.5, 8, continuing on. So the common difference is to subtract 0.5. The first term is 10. So as a point, we can write that as 1 comma 10. So explicitly, that's a sub n minus 10 equals negative 0.5 times n minus 1, which solving for a sub n is equal to 10 minus 0.5 times n minus 1. Now recursively, we start by defining the first term, so a sub 1 equals 10, and then we need to relate the terms together. So if I want the next term of the sequence, a sub n, I take the term before it, which is a sub n minus 1, and we notice that the common difference was to subtract 0.5. So we subtract 0, need a better 0 there, 0.5. And here we have our recursive definition. So this is a nice way to end because we get to tie everything together for arithmetic sequences. So first, an arithmetic sequence is one where we notice the pattern is adding or subtracting by a constant value from one term to the next. We call that the common difference, and we denote it with a lowercase d. Recursively, we need to define the first term and then a relationship between consecutive terms of the sequence. Explicitly, we're going to treat it like a line, identify the common difference, which will be the slope, identify a term. Most of the ones that we dealt with, we identified the first term. We can express it as a point. Then we just have to use our subscript notation when we're writing it out. So a sub n minus 10 equals negative 0.5 times n minus 1. And we solve for a sub n. So we have that linear function. Explicit is really good if we want to find a much higher term of the sequence. If I want the 100th, if I want the 1000th term of the sequence, explicit formula is the way to go. If I want to just know what the pattern is, well, recursive, I know I start at 10 and I'm subtracting by 0.5 every time. A little bit easier to identify recursively. But they both have their advantages and their disadvantages. But our main focus from this video was the explicit formula. So now I want you to practice with this explicit formula before you move into the second video on arithmetic sequences. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.